Hi, everyone. Welcome to my final PhD defense. Thank you all for joining. So my dissertation is called Classical Coding Approaches to Quantum Applications. So I'm going to talk about two prominent quantum applications and how we connect them to classical coding theory. So this talk is based on several papers, and I was fortunate to collaborate with several people in these different papers. So first of all, my advisors Henry Pfister and Robert Calderman. Saikat Guha is a professor at University of Arizona. He has also joined for this talk. And his postdoc is Kaushik Seshadrisan. So we worked on a quantum communication problem. And Swanand Kade is a postdoc right now in Berkeley. So we worked together on a paper. And Michael Newman is a postdoc currently with Ken Brown. We also worked on one of the recent papers we wrote. So let me get started with where quantum computing is today. So on the screen you will see like the prominent players in the field right now. So quantum computing and quantum information sort of started in the late 80s and the early 90s. And one of the exciting things that sort of kickstarted the interest in the field was Peter Shor's algorithm, which you might be aware of. So he showed that you can factor numbers at an exponentially faster rate, faster speed using a quantum computer than the best known classical algorithms. And factoring large integers is very crucial for public key crypto systems. And so a lot of people got interested in that, sort of kickstarted the interest in the field. Now today we are not yet able to perform Shor's algorithm with a lot of accuracy, and that will probably take at least a decade. But it is still a very exciting period because quantum computing is not like a lab experiment. We actually have companies that are building these systems. So some of the prominent names are D-Wave, which is a Canadian company. They have built a quantum computer that uses something called quantum annealing to solve some specific type of problems. And then there's other players. So IBM and Google are building like a quantum computer that is based on the circuit model. So they don't do quantum annealing, they do the circuit model of quantum computing. And they use a technology called superconducting qubits. And then we have IonQ, which is a startup company. It was started by Jung-Sang Kim. He's a professor at Duke, and he's also in this talk. He and another professor, Christopher Monroe, in University of Maryland, started this company, and they are building a quantum computer that is not using superconducting qubits, but by trapping ions in vacuum. So these are sort of like, so superconducting qubits and ion traps are sort of the prominent technologies. And so right now we have real systems, and we even have open source access to IBM computers and soon on these other systems. Now, one of the most exciting results in the recent times is this experiment that Google conducted called the quantum supremacy experiment. So there, what they showed is that they have a processor called the Sycamore processor, which has 53 qubits. And so the vector space in which you're computing is like 2 to the 53, which is very large. And so so roughly speaking, they showed that they did an experiment where they sampled random circuits, and then they computed the statistics of taking samples from the output distribution produced by the circuits. And so they are able to sample the output, and then they verified this statistically on a classical computer. And then they were able to show that their quantum computer, as I highlighted here, takes about 200 seconds to sample a million times. Whereas by their calculations, this would take approximately like 10,000 years on a classical best supercomputer we have. So this was a very exciting result, but IBM sort of debated on the specifics of the result in terms of whether it would actually take 10,000 years or whether you can do something smarter in like the IBM Summit computer, which is the largest supercomputer. And so there are some numbers game that is being played, but otherwise it's still a great technological feat where people have actually put together this kind of a system and showed this experiment and showed like a computational advantage. Now, two things I want to highlight are, first, the circuit that they actually sampled is a random circuit, and it's noisy. So it's noisy, so they're not doing error correction, and I'll explain what error correction is soon. So most of the computers today don't use quantum error correction. The other thing is that this is a random circuit, so it is not really useful for any specific practical task. So that brings to sort of two central questions you might want to have in mind for this talk. So one is quantum technologies promise a lot of computational advantages in several applications, but what applications are useful and what can be done in the near term? And then how do you tackle this noise or in other words, how do you do error correction? Now, if we take the noise problem, it was shown in the 90s. So until the 90s, people thought that noise was a fundamental bottleneck to building a reliable quantum computer. So just like analog classical computers, have a continuum of noise, and you can't always correct them. People thought that also applies to quantum computers, and so you might not be able to tackle the noise. And then in a few papers, several people, including Kaldabang, Shor, Steen, showed that you can use ideas from classical error correction, which we routinely use in wireless communication, data storage, etc. So you can use these classical coding ideas to actually correct errors in the quantum case. So this was a huge result in the mid to late 90s, and this is what showed that the noise is not a fundamental bottleneck. If you can design clever classic codes that are borrowed from ideas in classical coding, then you can actually decode, correct these errors. So that was like the first sort of classical coding connection to quantum computing. And then there's the other application, not computing, but communication. So let's say you have a quantum channel and you want to transmit classical information through it, and the channel is noisy. So how do you transmit information reliably? And so people have again used the classical coding idea of Pola codes, which are an exciting class of codes, and they showed that you can use these codes to reliably transmit information. Now, these are the existing sort of prominent connections to classical coding. And in this talk, I'll show you that we can actually strengthen this bridge to classical coding. So briefly, my talk is going to be in 2 parts. So the first part will be about quantum computing, where I'll show a sequence of results that we were able to show. And as building up with those results, we are finally able to come up with a new classical coding problem, which people had not thought of before, which is fundamentally motivated by fault tolerance considerations in quantum computing. So this is sort of another exciting coding connection, classical coding connection. And then I'll also show that if you want to benchmark quantum systems, then you can use classical codes in a different way, where you're not necessarily performing error correction in the quantum case, but you're still using these coding ideas to help you benchmark quantum computers. So I'll only briefly talk about that. And in the second part, I'll talk about how you can use this algorithm called belief propagation from the classical world again, and then use it in a quantum setting where you can transmit information through quantum channels. So that's the plan for this talk. And so it's split into 2 parts. I'll start with the first part now. So I'll talk about this, some basics, and then I'll talk about this logical Clifford synthesis. And then I'll talk about something called QFD gates, and then I'll show how you can get this classical coding problem using these tools. Right. So let me set up the problem clearly. So let's say you have some information stored in qubits. So you have k qubits of information. That's what this L subscript means. It's like logical information. Then you want to do some operation on your information. So the information on your qubits. And so you have some new state, which I call x tilde. Now the problem is all the operations you do in the lab are noisy. So if you don't protect from noise, then most likely the final state will not be the state that you want. So what we do is we encode your information in a quantum error correcting code. So you have k qubits of information, and you encode it into n qubits, where n is larger than k. So you add some redundancy to your data. And then you do, again, noisy operations in the lab. Now these noisy operations only act on the n qubits in the lab. And so you have to make this sort of fault tolerant. And because the code has some redundancy, you can use that to help correct some errors. And after you're done, you can decode, and hopefully you will be in the state that you desired. So this diagram should commute, is the point. And if you want to do that, then it's clear that for any operation that you want to do on your logical information here, you have to translate that to a physical operation that you can actually do in the lab. So remember that these n qubits in the lab is what you actually see and is what you can actually operate on. These k qubits live in the abstract. So they are sort of lost in entanglement, so to speak. And so the key problem that I'll talk about is this logical to physical translation. I hope that was clear. And so clearly, if you want to do this, then see that, so you note that any physical operation you do has to take a code state into another code state. So you have to make sure that you preserve the code space. And therefore, a fundamental question you want to have in mind is, how should I design my code such that the operations I like to do in the lab actually map code states to code states? So that is sort of a central question here. And here is our overall strategy. It's helpful to keep this in mind throughout the first part of the talk. So the key idea is that something that I'll define now called poly matrices or poly operators form an orthonormal basis for all operators. So you can express everything as a sum of polys. And so we do that, and then we look at how these acts on, so we understand the action of these, any lab operation you want to do, so gates. So just as a terminology, so gates or circuits or operations all mean the same as far as this talk is concerned. So we understand the action of gates you do in the lab on the poly matrices, and then use that to characterize how they affect quantum codes. And then finally, we want to restrict to things that are reliable in the lab or fault tolerant in the lab. So that will be our strategy for this talk. Okay, so now with that motivation, let me introduce some basics. So I'm just assuming that some of my audience might not be familiar with the quantum formalism, so I'm just going to go over some essential basics. So a qubit is your quantum equivalent of a bit. So a classical bit can only be 0 or 1, whereas a qubit is a two-dimensional vector space. So it's a length 2 vector with two complex numbers, alpha and beta, and the squares sum to 1. Now, we very well know from linear algebra that for a two-dimensional vector space, the standard vectors, basis vectors are these two. And in quantum notation, we actually call this vector the 0 state and this vector the 1 state. And this represents what's called the Kronecker product. So, so when you take Kronecker product of these two, you replace this 1 by this 1 times this vector. And so that's why you get 0, 1 here. And then 0 times 0, 1 is 0, 0. And what you see here is that, so it's a length 4 vector. So you can index the entries by 0, 0, 0, 1, 1, 0, and 1, 1. And this label 0, 1, which is the same here, tells you where the 1 is present. So these are your basis vectors when you have 2 qubits. And similarly, another basis vector is 1 Kronecker 0, and you have 1 here. And similarly, there are 2 more basis vectors, and those will be your basis vectors for 2 qubits. And similarly, you can extend to any number of qubits, and then you take any quantum state on n qubits as a complex linear combination of your basis states. So that's what qubits mean. Now, with the definition of qubits, let's move to the poly operators that I mentioned before. So for a single qubit, the poly matrices are just identity x, which is called the bit flip, because it flips from the 0 state to 1 state and 1 state to 0 state. Z is called the phase flip, because on 0 state, it does not do anything. On the 1 state, it picks up a phase -1. And Y is just a combination of both with an overall phase I for technical purposes. And so these 4 matrices with some overall phases generate what's called the poly group. The key structure in the group is that the X and Z anti-commute. So the order in which you apply these gates matters. So if you do Z first and X second, that's not the same as X first and Z second. You have to take care of this minus sign. Okay, so just like for qubits, we took Kronecker products of basis states. For n qubits, the n qubit poly group is again Kronecker products of these 4 matrices. So here is an example. So I have 3 qubits. I have 1 qubit in 0 state and 2 other qubits in 1 state. And if you have 3 poly operators, you apply each poly operator to the corresponding qubit. So X applied on 0 is 1, Z applied on 1 is -1, Y applied on 1 is a combination of both, so you get this state. So hopefully this notation is clear. And the fact that you want to keep in mind is that you can express any n by n matrix, complex matrix, as a sum of poly matrices. So poly matrices form a basis, and that's what we are trying to exploit. Okay, So it's convenient to actually use sort of a shorthand notation for polymatrices. So, so for every polymatrix, say on 3 qubits, we represent it by 2 binary vectors A and B. So I call A the X component and B the Z component, and the naming will be clear now. So let's pick this example. So I have 3 qubits. I'm applying X on the first qubit, Z on the second, Y on the third. So because I'm only applying X, only the X component is 1. Because here I'm only applying Z, only the Z component is 1. Because here I'm applying both X and Z, I have both components 1. So by 2 binary vectors of length n, you can represent any polymatrix, basically. And so you can basically think of polymatrices as pairs of binary vectors. And we saw in the last slide that polymatrices commute or anti-commute, the minus sign. And in the binary vector space, in this binary vector notation, if you have 2 polymatrices, then you can define this kind of inner product. So these are row vectors, and so this is an inner product. And if the inner product is 0, then the matrices commute, and if the inner product is 1, they anti-commute. Now, once you have defined the poly group, so the Clifford group is defined by the action that it maps polymatrices to polymatrices under conjugation. So what do I mean by conjugation? If you take any polymatrix, you left multiply by a Clifford, and you right multiply by its inverse. But now the G is actually a unitary matrix, and so the inverse is just the Hermitian transpose, and so that's called conjugation. And when you conjugate, you get a new polymatrix defined by a binary vector, which is the original binary vector times this matrix F. And this matrix F preserves this inner product, and so it has to satisfy this constraint, and it's called a symplectic matrix. So just the essential thing from this slide is that you can think of polymatrices as binary vectors and Clifford matrices as Clifford operators as these binary symplectic matrices. Okay, so I introduced a bunch of things, so let's just do an example. So control Z is a 2-qubit Clifford operator. So this is the unitary matrix representing the operator. You can do a calculation and show that if you conjugate this polymatrix by the control Z, you get X tensor Z. Now let's fill in the details. So X tensor I can be represented as this binary vector, so X on the first qubit and nothing anywhere else. And using this representation, we know that the result of conjugation is this times some matrix F. But we know the answer in this case. We know it's X tensor Z, so you can write down the actual answer in the binary notation. And so you see that this times F should give you this vector. And so we can write down this F matrix such that the first row is what you want. And similarly, if you do it for I tensor X, Z tensor I, and I Kronecker Z, you can write down all the rows of this matrix. So basically, you can think of this control Z as just this binary matrix. Right. So another thing I want to introduce is called stabilizer codes. So the code is defined by a stabilizer group, which is generated by R commuting polymatrices. And you have to make sure that minus the identity is not in the group. The stabilizer code is given as the subspace of all complex vectors such that they are +1 eigenvectors of G. So if you add any stabilizer group element on the state, you just get the state back. And so that's how the code is defined. So it's a subspace of this vector space. So here is an example. So here is a 642 code. So I have 2 generators. So my R is 2. And so the number of qubits I can encode into this code is 6 minus 2, which is 4. So I've encoded 4 qubits of information in 6 qubits of information in 6 qubits. And so these are the 2 generators. And if you write a generator matrix for this group in the binary notation, so then X tensor X Kronecker 6 is just X everywhere and no Z's, and Z Kronecker is 6 is Z everywhere and no X's. And anytime that you can write a generator matrix which splits into this block form where these things are 0 is called a CSS code. All right. So what is our goal? We want to do arbitrary quantum computing. So you encode k qubits into n qubits, and you want to be able to do any quantum operation on these k qubits by operating on the n physical qubits in the lab. Now the nice thing is that it's hard to think of everything at once, so you can actually break it down. So it's a well-known fact that if you only do Clifford gates and any one non-Clifford gate, then putting these together, you can approximate any unitary operation you want up to an arbitrary precision. So all you have to care about is Clifford and one non-Clifford. So let's start with Cliffords first. So let's see an algorithm that can give you physical circuits that you can do in the lab that realize any desired logical Clifford gate. Okay, so here's the first contribution from my dissertation. So think of this LCS algorithm as a black box. So the first thing that you do is you initialize the algorithm with two things. So the first thing you do is you input a stabilizer description. So in this case, I did the 642 example. So you input these stabilizer generators, and then you can find logical poly operators for your code. So you have 4 qubits, and you want to be, the basic thing you want to be able to do is do poly operations on these 4 qubits, but you are restricted to 6 qubits in the lab. So you can only do things on these 6 qubits, and they have to induce the right action on the 4 qubits. And there are standard algorithms to find logical poly operators. So you do that and you compute this, and you feed that into the algorithm as well. So that is the initialization phase. After that, you describe any Clifford circuit that you want to do. In this case, I picked a simple example. So we saw the control Z gate as an example a few slides back. So let's say you want to do control Z on the first and second logical qubit out of the 4. So you feed that into the algorithm. What the algorithm gives you is all 6 qubit Clifford circuits. So all 6 qubit Clifford circuits up to some equivalence relation that realize this particular operation on the first and second logical qubit. So it's a general algorithm. It works for any stabilizer code, and it's efficient because it uses these symplectic matrices, as I'll briefly mention soon. Okay, so that's about the algorithm. So the only caution I want to make is that you can use this algorithm to find physical circuits that do any logical Clifford on any stabilizer code, but the algorithm does not guarantee that the circuits that you implement in the lab are fault tolerant, meaning like noise can still break your circuits, and that's something we are investigating still. Okay, so something in relation to the algorithm that I want to mention is the point about benchmarking that I made earlier. So if you want to benchmark a quantum computer or for other applications in quantum information, you usually need something called as a unitary 2 design. So what does it mean? It's just a collection of unitary operators such that if you take the status and with a distribution, so it's a collection of unitary matrices with a distribution, with a discrete probability distribution on them. Then the first and second statistical moments of the distribution matches the Haar measure on the full group of unitary matrices. So the full group of unitary matrices is huge, and you can think of the Haar measure as just the uniform distribution on the full unitary group. And the 2 design says that if you only care about the first and second moment, then you don't need all unitaries. You just need a collection, a subset of unitary matrices that satisfy this property. Again, so this is very useful in benchmarking, and we actually use some classical codes to actually construct such a 2 design. So I just want to briefly mention that. So a Coulomb set is a specific collection of binary symmetric matrices. I won't get into the details here. And then you can define a Coulomb code that is specified by 3 things. So every code word in the code can be indexed using 3 things. One is a symmetric matrix from this Coulomb set, and then any binary vector W, and then any scalar from the ring of integers mod 4. So Z4 is just 0, 1, 2, 3. It's a set of 4 elements. So yeah, any 3 combinations you pick gives you a code word in the code. And so you can count that there are these many code words. And this was actually a code that was developed by somebody called Coulomb in the 70s. And then what you do is you do this simple trick. So every element of this code word, is in Z4. So every element is either 0, 1, 2, or 3. And then you can map that into this set. So this is just the complex number I raised to the power 0. So I to the 0 is 1, I to the 1 is I squared is -1, I cubed is -I. So you just made this simple mapping from 0, 1, 2, 3 to this set. And that gives you an interesting set of pure states. So I introduced pure states at the beginning of the talk. And this gives you something called graph states, which are a specifically nice collection of pure states, which have many applications in quantum information. So you can get graph states using this procedure. And then we show the main result in our paper, in this paper here, is that the symmetry group of this graph states, defined in a proper way, produces a unitary 2 design. So the main thing I want to emphasize here is that I'm using classical codes, so specifically this code, to construct something called as a unitary 2 design. And so I'm not actually doing quantum error correction. So all existing sort of connections to classical coding are using classical coding ideas to do quantum codes. But here I'm not really doing any quantum code, I'm just doing this 2 design. And the other thing I want to mention is that you can combine this with the LCS algorithm that I introduced in the previous slide to do a logical 2 design. So what do I mean by that? So you can use this procedure, for example, to construct a 2 design on these 4 qubits, but now you've encoded them into this code. So if you actually want to implement the 2 design in the lab, you can only do 6 qubit circuits. And so you can use this algorithm to translate the 2 design from this space to a 6 qubit circuit in this space. Okay, so that's what I'll mention there. Let's get back to the LCS algorithm. So the key idea there is again to use this representation we know for Cliffords. So you can, because polymatrices form a basis, you can define your desired operator, G, by how it acts on the polymatrices on the logical qubits. And then you translate them to the physical space. And then, like I said in the beginning, you have to make sure that your operation preserves the code space. So for a stabilizer code, that means the stabilizer group should be unchanged before and after you do the operation. So that means for a Clifford circuit in the lab, it has to map stabilizers to stabilizers. And all of these are conjugation constraints. And so you can sort of rephrase them as symplectic linear constraints on this target matrix F. So remember, this F is a binary symplectic matrix, and it's a 2n by 2n matrix. So if you have n qubits, it's 2n by 2n. So it basically has like roughly n squared entries, whereas a Clifford unitary matrix will have 2 to the n by 2 to the n. So it's sort of 2 to the 2n entries. So there's a huge savings in complexity here because we are working with these binary symplectic matrices. And so that's why the algorithm is efficient and this all works. Now let's see how we might try to extend this to non-Clifford gates, because remember that Clifford alone is not enough. So you have to do at least one non-Clifford gate. The problem with non-Cliffords is that there is no clear symplectic connection. So here we have this symplectic matrix that represents the Clifford circuit, whereas here we don't have a clear symplectic connection. So that's the first problem we face. And the second problem is that, so here we said you have to map stabilizers to stabilizers. So the stabilizer group should be unchanged. But we know that if your operation in the lab is not Clifford, then when you conjugate a polymatrix, so remember all stabilizers are polymatrices. So when you conjugate a polymatrix by a non-Clifford operation, then you're not guaranteed that the result is a polymatrix. So it's not clear how you can map stabilizers to stabilizers if you use a non-Clifford gate. And so that's the problem we face. And so that brings me to our second contribution called QFD gates. Okay. All right. So here are the standard operations we do in the lab. So I obviously don't want you to remember everything here. So I've split it into 2 parts. So Clifford, like I said, is not universal. So these are all the standard Clifford operations. And this T gate is like the simplest non-Clifford operation you can think of. So if you can do any Clifford and this non-Clifford, then you're universal. Okay. And so because polymatrices form a basis, we can characterize each of these gates by how they act on polys. Now what I want to focus on is gates that look like this. So remember again the control Z example we did earlier. So you can write down this control Z, which is a diagonal unitary matrix. So this just means diagonal. And the diagonal entries look like this. So it's the complex number I raised to a quadratic form. So this V or V transpose is a quadratic form. And so this is a form we particularly like. And we know that this is the symplectic matrix corresponding to this unitary matrix. Now, if we take the T gate, we know how it acts on polys, but we don't have a symplectic connection because it's not Clifford. The question is there any way to reasonably fill this gap so that we may be able to extend our LCS algorithm to non-Cliffords. And that's exactly what I'm going to show now. So again, so I've just reorganized the information I gave you in the previous slide. So you have sort of a hierarchy of gates. So the first level is the poly operators. The second level is the Clifford operators. And here I'm only focusing on diagonal Clifford operators. Now, what these authors showed in this paper is that if you are a unitary operator living in this hierarchy, so I'll reveal something more in the hierarchy. So if you're in the hierarchy and you're diagonal, then your diagonal entries have to be a 2 to the nth root of unity. So here you see that this number here is a 4th root of unity. So if you take this, I to the 4 is 1. So this is a 4th root of unity, but any operator in this hierarchy has to be a 2 to the nth root of unity is what they showed. Now, so these are our standard Clifford examples. Now let's try to extend to non-Cliffords. So any level L, we look at gates that are diagonal, but now I replace this 4th root of unity by a 2 to the nth root of unity. So that's this Z. But I retain the quadratic form in the exponent. The only change is that now R has integer entries modulo 2 to the L instead of having binary entries like in the Clifford case. So this is the phase gate, that's Clifford, and this is the symmetric matrix for it over Z4. But now I have extended this to the higher level. So on the 3rd level, you have the T gate, which we saw in the previous slide. It turns out that the symmetric matrix is the same, but now you look over Z8, so integers modulo 8. And similarly, you can extend this control Z gate to a controlled phase gate. So the symmetric matrix looks the same, but now it's instead of Z4, you have Z8. And the unitary matrix is just the square root of this. So square root of -1 is I. So, okay, so what I want to overall tell here is that we have defined this class of diagonal gates that live in this hierarchy called the Clifford hierarchy. And they are 2 to the nth roots of unity raised to some exponent that is a quadratic form. And so we call them quadratic form diagonal gates. Now, what are we, again, so emphasizing what I said in the beginning of the talk, we want to understand how they act on poly matrices. Now for Cliffords, we have this nice representation. So what happens for these QFT gates? So it turns out that if you take a poly matrix and conjugate by a QFT operation, then you still get an overall phase. Like instead of the plus or minus, you have this phase here. And then you get a new poly matrix, just like here. And then you get a recursion to a lower level gate. So that's the new thing that happens that was not here. So this is a natural extension to the symplectic formalism because this matrix here is still symplectic. And we are able to show that canonical products of all 1 and 2 qubit gates, which I call 1 and 2 local gates, are QFT. So they all look like this thing that we introduced. And Mormon-Sorensen gates are the standard 2 qubit gate that you do in the lab for ion trap quantum computing. And we can quite easily show that they are also QFT up to some Hardeman operations. So the key thing here is this result, that if you conjugate by a QFT operation, you get an overall phase, a new poly matrix, and a recursion to a lower level QFT gate. Now I'm going to use that to do something useful. Okay, so again, this slide should be familiar now that I have replaced all Cliffords by non-Clifford. So now we have done the first part, and now I want to do non-Clifford gates, but we saw it is hard, but our strategy is still the same. We are going to understand the action on poly operators, and that's exactly what I showed you with the QFT formalism now. So what are we doing? So these are the problems we faced. So no clear symplectic connection and this problem. Our solution is that for QFT gates, you do have a symplectic connection now, and you don't have to map stabilizers to stabilizers. All you care about is preserving the code subspace, which means you preserve the projector onto the code subspace. So instead of looking at the stabilizer, look at the projector. So what we're doing here is sort of reversing our LCS strategy. So for LCS, we took a logical operation, and then we used the LCS algorithm to translate it to a physical operation in the lab. Now for non-Cliffords, we find this a little hard to do. So we reverse the strategy. So we fix a physical operation that we want to do in the lab, and we ask, how should I design my code so that it actually induces a logical operation? So this is a reverse strategy. and I'm going to focus on T gates. So I'm going to say, in my lab, I have n qubits, and I'm going to do T gates on them. How should I design my code such that this operation that I do with T gates maps code states to code states? So that's the question at a high level. Let's formalize that mathematically. So this is the question. So when transversal just means I do T on every physical qubit in the lab, so on every n qubit. So let's say I pick a stabilizer group. I can write down the projector onto the subspace defined by this group. It's just a summation over every element in the group up to some plus or minus 1 signs. That's the code projector. And remember, what we were interested in is preserving this code projector before and after the operation. And a useful thing to do there is first to understand when you do transversal T, so T on all qubits, and if you conjugate a polymatrix, what does the result look like? And so you can, so T, like we saw before, is a QFT gate. And just to remind you, let me go back. So here, so for example, you can think of this as T on all qubits, and you're conjugating a polymatrix. You can use this expression that we derived, but it's sort of in a product form. So it's like this times this times this. But what we would really like is to expand this right-hand side in the poly basis. We saw that poly matrices form a basis. So we want to express this right-hand side as a linear combination of poly matrices. And that's exactly what I've done here. So I've conjugated the poly matrix, but on the right side, I'm expressing as a sum of poly matrices. And so you can think of this as sort of a Fourier transform. Now, what does this represent? This represents the Hamming weight of this binary vector A. So it's just the number of ones in this vector. And this symbol means that both Y and A are binary vectors. So this means that the support of Y is inside the support of A. Meaning that if Y has a 1 in a particular position, then A should also have a 1 there. Anyway, so overall, this is the result. And now we want to understand, when does transversal T preserve my code projector? So if I conjugate the code projector, it should remain unchanged. And so if you go back here, and if you conjugate the code projector, by linearity, you're conjugating each term. And that's exactly the thing we derived here. So you can just plug this in, and so you get this full expression. So you have this giant thing on the left-hand side, and it should be equal to your original code projector. And solving, so first of all, solving for a linear combination like this, for a general QFD operation could be hard. For transversal T, it turned out to be doable. And similarly, solving for conditions when this equality holds can also be hard in general, but we solved this completely for the T case. I'm not going to give you the general theorem, but I'm going to just give you the special case for CSS codes because it's easier to describe. So CSS codes, remember, this is where the stabilizer matrix has a block form. So you basically have two classical codes that describe the code. So one lives inside the other. The first condition is that every vector, every code word in this code C2 has to have even number of ones. And the second condition is, for every code word you pick from C2, this code, so C1 perpendicular, which is actually the code that is dual to the C1, must consist of a self-dual code that is supported on X. So for example, let's say X is like 101101, which means the indices of non-zero entries are like 1, 3, 4, and 6. So it's like 10, 1101. So the non-zero entries are in positions 1, 3, 4, and 6. And so what this thing says is that then C1 dual has to have a self-dual code that is supported on the positions 1, 3, 4, and 6. So that's what this condition says. And this is motivated by fault tolerance because this comes out of transversal T, and transversal T is naturally fault tolerant. Okay, so once you design this code, then using parameters for these codes C1 and C2, you can write down the parameters for your quantum code. And so this is like a new classical coding problem because everything here is basically classical. So you're only dealing with binary codes here. Now we are able to prove two interesting corollaries from our main result. So one is that if you want to do T gates on all qubits in the lab, and you want that to induce T gates on all the encoded qubits in the code, Then the only CSS family is these tri-orthogonal codes. And these were introduced by Sergey Bravy and Jungwon Ha. And these are a popular family of codes. So they showed that this construction is sufficient for this property. We sort of prove a converse and show that it's also necessary. And if you look at non-degenerate stabilizer codes, non-degenerate meaning every stabilizer has weight at least D, then we show that you don't get much by thinking beyond CSS codes. So for every NKD non-degenerate code with the transversal T property, we can also produce a CSS code with the same property. So this is sort of like an open problem people have been thinking of whether CSS codes are enough, or do we actually gain more if we work with non-CSS stabilizer codes? And this sort of settles the question under this assumption of non-degeneracy. So the open problem that I first advertised, the classical coding open problem, is produce a CSST family, meaning a pair of classical codes satisfying these constraints, such that the rate of the code family is asymptotically linear. So the number of encoder qubits grows linearly with n. And similarly, the code distance should also grow linearly with n. And so this is a very hard problem, and we even doubt if such a family exists. But if we can prove that such a family exists, then we can show something like we can do constant overhead magic state distillation. And this is an important protocol for doing universal quantum computing. And this would basically mean a tremendous decrease in resources. So this is a very nice open problem that comes out of a classical coding connection that is inspired by transversality. And this is the third contribution. And I'll now wrap up the first part. So first I reviewed the LCS algorithm. Then I defined something called QFT gates and showed how they act on Pauli matrices. Then we used that formalism to construct quantum codes that support T gates in the lab. And we proved some interesting corollaries. So things that I couldn't talk about but are in the paper are some extensions to finer angle Z rotations, so not just T gates. And we give some Reed-Muller code families that satisfy this property, but they don't satisfy this linear rate and distance property. They are a CSST family. And so there are many interesting questions to think about. One is, can we extend this to arbitrary QFT gates? So let's say you want to do a gate in the lab, and let's suppose that it's a QFT gate, and it's super reliable. So let's say it's super reliable in the lab, and so you want to extract the maximum out of the operation. That's your strength in the lab. And so what we did for T gates also hints at a recipe for any general QFT gate, but whether can we solve it in general is still open. So the main takeaway I want to give from this part of the talk is that thinking of unitary operators as linear combination of Paulis is a very useful trick. It is not new, like we didn't introduce it, but it seems to have not been utilized as much. Okay, so that's wraps up the first part. Now I'm going to go to the second part. Give me a moment, I'll just get some water.
Now might be a good time, if there are any questions about the first part, to take questions.
Does anyone have questions?
All right, if not, just thought I would throw that out there.
All right, so I'll continue with the second part. Okay, so message passing algorithms are well-known classical algorithms. So they are useful algorithms because they can efficiently compute certain quantities when you can define a problem on a graph. So you have a graph which has a bunch of nodes and edges connecting the nodes. And if you can sort of pose your problem on a graph, then there's a good chance that there might be a message passing algorithm that can compute certain quantities on the graph which are relevant to your problem. A specific well-known algorithm is called belief propagation. So where do you use it? So you use it for statistical inference problems, which means, for example, like in a coding scenario, let's say you have a channel, you transmit a classical code, you get some observations from the channel, And based on the observations, you want to optimally decide which code word was transmitted. So that's like an inference problem, because you're having an observation at the receiver side, and based on the observation, you want to estimate the information that was transmitted optimally. So in problems like this, for problems like this, belief propagation can be used. And if your graph is a tree, then this is actually optimal in terms of getting the lowest possible probability of error. Now, when the graph is not a tree, you cannot prove such a strong result, but empirically, we usually see that it actually works quite well in many cases. And belief propagation is an algorithm that is routinely used in cell phones and storage devices for error correction. So yeah. Now, one sort of theoretical question you can ask is, belief propagation is an algorithm that passes sort of probabilities as messages. So it's a specific message passing algorithm where the messages are probabilities. Now, a natural question to think about is, what if I replace probabilities with quantum information? So is there a reasonable algorithm that can do such a thing? And can I use it for some useful application? Now, this might look like a theoretical question, but actually, if you can do something like that, then you might have some significant advantages in communication over quantum channels. And we'll see one such application today. So the algorithm I'm going to be talking about is called belief propagation with quantum messages. It was introduced by Joseph Rennes at ETH Zurich. So he defined this BP algorithm that passes quantum messages. So it passes qubits as messages. And he shows that you can actually decode binary codes over certain quantum channels called pure state channels. Now, at a high level, what application am I thinking of? So in sort of free space, like laser communications, so the actual channel you have is a quantum channel. So when you transmit information, you sort of transmit classical information. At the receiver, you actually get quantum states. So for every bit of information, you actually get a quantum state at the receiver. Now you need to know how to process this quantum information in order to decode the classical bit. And so this is a concrete practical setting where you might actually employ this algorithm. And in this talk, because of time, I'll only sort of motivate how the algorithm works. I won't get into too many details because of lack of time. But towards the end, I'll show that it has some very good performance, and that's why we care about it. So let me start with classical belief propagation. So as most of you might know, a classical binary code is defined by what's called a parity check matrix. The code is just the null space of the matrix in the binary vector space. So every code word is orthogonal to every row of the parity check matrix. So such a code encodes k bits into n bits. And so one example is this 532 code. So it encodes 3 bits in 5 bits. And the parity check matrix looks like this. So what does the first row impose? It says that the first bit plus second bit plus third bit should be 0 modulo 2. And a graphical way to represent that is to put a check node or factor node called C1, which is the first row. And every node attached to it, in this case x1, x2, x3, should sum to 0 mod 2. And similarly, the second constraint is that x1, x4, x5, x1, x4, x5 should sum to 0 mod 2. And so that's called the factor graph representation of this linear code. And these WIs represent channels. So they're just transition probability. So a classical channel is described by a transition probability matrix, where you say if I transmit bit xi and if I receive yi, then this is the probability. Now, okay, so going back to our problem, we transmit a code word through n uses of the channel. We receive a vector y, which belongs to some alphabet. It doesn't have to be binary. And you want to optimally estimate which code word was transmitted. So the standard base thing you can do is to say, I observe y, and I want to find the probability of transmitting the code word x, given that I observed y. And you can use standard probability to write this down. And so first of all, P of y given x, if I assume the channel is memoryless, then if I say transmit 5 bits, like in the example, then those 5 bits are 5 independent uses of the channel. And so it's a product of 5 probabilities given by the channel transition probabilities. And then the probability of transmitting that code word is, first of all, it has to be in the code. So this is just an indicator function, which is 1 or 0. So it's 1 if X is a code word, it is 0 if it's not, because you only care about code words. And if it's in the code, then you are uniformly picking among all code words. So this is the uniform probability. Now we are just going to optimize for the best X, and the denominator is not dependent on X, so you can just drop it and just put this proportionality symbol, and you still have this product of probabilities. And the indicator function for X being a code word is just checking these two parities. You check this parity and this parity. So you can split it into two indicator functions and then rearrange them to group the same bits together. So here it only involves x1, x2, x3. So you combine with x2, x3, and here x4, x5. And the optimal decision is to find the code word for which this number is the maximum. And that's called the block maximum a posteriori decoder. So it's called the block map decoder. And this is optimal if you care about minimizing the probability of error, the average probability of error. Okay, so that's all good. But the problem is, if you think about this thing, you have to compute this number for every code word. And the number of code words you have is 2 to the k. So it's actually, so the complexity is exponential in k. And so you want to try and decrease complexity for practical reasons. So one thing we can do is, instead of doing block map, we can make bitwise decisions. So you take the full posterior probability and you marginalize out all other variables, and you only keep one variable, in this case x1, and then you can sort of rearrange and group things. But basically here you're optimally deciding if x1 is 0 or 1 based on its posterior, so the posterior marginal distribution. What BP does is it does bitmap, but it does it efficiently. So key thing to note here is that this graph is a tree, and so this sum in red can be computed at this node, and it's local. So you can just locally compute this sum here based on messages from x2, x3. And again, based on messages from x4, x5, you can locally compute this sum at this node. And you can do this in parallel because they don't talk to each other. And in the next step, you combine the message from here, which is this summation, and this message from here, which is this summation, and you multiply it from the channel observation, that is this guy. So at a check node, you do this local sum. At a variable node, you just multiply things together. And this is exactly what BP does. And it's called belief propagation because this is sort of like a belief of this bit being 0 or 1. So these two are independent beliefs of this bit being 0 or 1. Now, what I want to sort of emphasize to understand the quantum message passing that Joe Wren has introduced is this sort of induced channel perspective. So let's just focus on one particular variable node, and let's say it's connected to two check nodes, and then you have a bunch of variables here. Now, because we know that these check nodes impose an even parity check, meaning that all bits connected to it have to sum to 0, we can just combine all the bits into one variable y. And clearly y plus x has to be 0 according to this check. And so y is basically an independent observation of x through some kind of channel w. This is an imaginary channel. And similarly, you can do this at the other node. So you have two independent observations for x, and you can put together a channel convolution, so to speak, where your output variable is actually a tuple, so it is y and z, and your input is just x. But because it was a tree, this is independent, and so the probability of getting y and z given x is just the probability of y given x times probability of z given x. And according to this local sort of induced channel that we just introduced, it's an abstract induced channel, you can actually see that BP is locally optimal for this local channel. So first of all, we saw that BP is globally optimal. So in the previous slide, we showed that if your graph is a tree, it does bit map on the tree. And so it's globally optimal. But here we also showed that by this induced channel, it's locally optimal. So you can verify that. And similarly, at a factor node or a check node, you can see that, so you have a check node, so you send x in, and you get this y and z out. But if you zoom in here at the check node, you have two variables u and v. And we know that u plus v plus x should be 0. So which means either u equals x and v equals 0, so that u plus v is x. So u equals x and v equals 0, or u equals x plus 1 and v is 1. Those are the two possibilities. And you can write down a channel convolution by this observation. So this whole thing put together is a sort of compound channel, where again the output is two variables y and z, which are independent observations of u and v, which we borrow from the previous slide. And so you can define this induced channel and again verify that at the variable node, when BP multiplies things at a check node, when BP computes this local sum, that's actually the local optimal procedure for this induced channel. So again, so I want to emphasize that, so the globally optimal nature of BP splits into local optimality in each of the nodes of the graph, as long as the graph is a tree. And this is the key observation that Rennes tried to generalize. So here you have these classical channel combining or channel convolutions. And for a quantum channel, he generalized this variable node convolution to this operation, where this is again a Kronecker product. Now W of X is a quantum state. It's not a probability. Whereas here it was a probability. And again, here you have a Kronecker product. Each of these things are quantum states instead of being probabilities. Okay, that's all very nice. It seems natural, but how do you actually define an algorithm that is based on this channel convolution? So BP is the well-defined algorithm for this channel convolution, and how do you actually do that for the quantum case? So Rennes's algorithm is only defined for a specific channel called this pure state channel. So you send in classical bits. So you send in x, 0 or 1, and the channel outputs one of two possible states, either theta or minus theta. Now, so theta is just a length 2 vector. It's a qubit. So you have cos theta. So it's two entries, cos theta over 2 and sin theta over 2, and theta is between 0 and pi over 2. And if you send a 1, you get minus theta. You get cos theta over 2, 0 minus sin theta over 2. And then you can see that these two states have this overlap of cos squared theta. So this is just the inner product squared. And you can see that the inner product squared is cos squared theta. So clearly, if theta was pi over 2, then life is great because the inner product is 0 and you can perfectly distinguish the two states. But if the inner product is not, if the angle is not pi over 2, then this inner product is non-zero and you cannot perfectly distinguish them. That's the key uncertainty in the channel. So I want to emphasize that the channel model doesn't have any noise. The only uncertainty at the receiver side is that if theta was not pi over 2, you don't know which bit was transmitted. You can't perfectly distinguish the two cases. Now, let's say Q is the prior probability of X being 0. Then you can write something called as the joint density matrix. So it's basically the quantum sort of equivalent of a probability distribution. So here I say with probability Q, I send 0 and I receive theta. And with probability 1 minus Q, I send 1 and receive minus theta. The capacity of this channel, which means the rate at which you can send information reliably, is given by this expression. So you can compute this quantity where F is the fidelity or the square of the overlap. And this is the binary entropy function. So you can compute this quantity, and this is the Holyover capacity for this particular channel. Now, at the receiver, at some point, you have to sort of interface the quantum information you get into classical information. So you have to convert them into bits. And what you do is measurement. So if you have two possible candidate states, Hellstrom defined the optimal measurement that you can use to distinguish the two states. So basically, he says that take rho 0 minus rho 1 and project onto the positive eigenspace. For this particular channel, you can see that it's proportional to X, the Pauli matrix. And so you just measure in the Pauli basis, Pauli X basis. What is the optimal probability of error? It is this expression. And for this particular channel, it turns out to be 1 minus sin theta over 2. So if I combine the channel and the measurement together, then you sent a bit, it went through the channel, you did a measurement. The measurement gave you a bit of information, 0 or 1. And overall, you just have a binary symmetric channel where the probability of flipping the transmitted bit is given by this. So overall, you just have a BSC. And you know the capacity for that binary symmetric channel, but it turns out that at some parameter regimes, theta, it can be much smaller than the Holyover capacity we calculated in the previous slide. And the question is, how do you close this gap? Well, we know that you cannot do single qubit measurements. So what we did here, just to be clear, let's say we use this 5-bit code I introduced before. So you sent 5 bits through the channel, and you received 5 qubits, and you use this Hellstrom measurement for each qubit. So each qubit, you again converted it into a bit. So overall, you just have a binary symmetric channel, and you used it 5 times. So that's the procedure we did, but that's suboptimal. What you actually have to do is optimize over all possible 5 qubit measurements. That's when you can close this gap. And this is what these Pola codes in the classical quantum setting actually do. But the decoder is complicated. It's a theoretical construct, and it's hard to actually build in the lab. So the question is, can you use this belief propagation idea to define a quantum BP algorithm that closes this gap? And this is sort of asymptotic. So capacity is an asymptotic thing. But if I give you a specific code, then can you define an algorithm that is optimal for that particular instance? So this is not asymptotic, and that's what I'll talk about now. So given a particular code, how do you define a quantum BP algorithm that is that optimally decides which code word was transmitted? Okay, and Renes's idea was that you use these channel convolutions to do it. So he basically defines operations you can do on these channel convolutions, and that's this picture. So for example, you receive qubits from the channel, and at a check node, we already know that the induced channel we defined before is given by this W box star W prime. That's what gets induced at this node and this node. And Renes says that you can do this U star, which is just a control knot. And if you do that at these qubits, then the resulting state is a classical quantum state. So you have some classical subsystem, and as a function of that index, you have one of 2 possible quantum states. And he says that you can just measure the classical subsystem and pass the resulting qubit and the measurement result as the message for the next stage. So here you basically do this control knot, and then what you get is 1 qubit of information and 1 bit of information. And again, so after you do that, here in the classical case, we just multiplied the probabilities, but here we have this channel convolution, and Renes defines this U circle star operation as a function of the parameters. And he says that at the result, you have basically pulled in all the information onto one system, and the other system is trivial. So you can just discard this system and pass this qubit as the message for the next stage. So based on that, you can actually write down the circuit, and this is just for decoding the first bit. So after you do the sequence of operations, you measure the first qubit, and that gives you the measurement for the first bit. And you just, this is just the expanded circuit. So starting from left all the way till this measurement is what we saw in the previous slide. And after this, we actually introduced this sort of new operation, which is not in Renes's algorithm, and it came out of analyzing this specific example. And then we invert everything we did for the first bit, and then do processing for the remaining qubits. And so that's the overall algorithm. I won't get into the details, but here is the final result. So like I said before, if you measure each qubit from the channel, so in this case, you send 5 bits. If you measure each of the 5 qubits at the receiver, and then on the resulting bit string that you get from the measurements, you get 5 bits of information. If you do, classical maximum a posteriori, so block map, then the blue curve is the best probability of error you can get. And so it's not hard to compute. And on the classical bits that you induced from the measurement, if you do classical BP, that's the probability of error you get. Now the fundamental quantum limit is given by this UN Kennedy lax conditions, and you can compute this purple curve from that. So that's the optimal probability of error in deciding which code word was transmitted through this channel. So that's the purple curve is the fundamental limit. And when we actually simulate this algorithm of Renes with our modification, then we actually see that it's right on top on this purple curve. So it's actually quantum optimal. And we also do extensive analysis to show why we should expect this curve. So the key takeaway here is that, and this is motivated by this optical communication setup where the right parameter is not theta, but something called as the mean photon number. You can roughly think of it as SNR. So it's like signal to noise ratio. So low mean photon number per mode is like low SNR, and this is like the relevant regime for free space laser communication. And so this is the quantum advantage that you get if you build this particular receiver compared to the receiver that is built today, which can only achieve the blue curve. And so the overall takeaway, I just want to summarize this part of the talk, is that we saw that BP does local inference over locally induced channels, and it's locally optimal. Using that, we saw a quantum algorithm that passes qubits as messages on the factor graph, and we have shown it's quantum optimal for the 5-bit code. So what does it mean practically? So if we can design a small sort of quantum computer that can process photons for these laser communications, and it has to only operate on 5 qubits, and you only have to build this specific circuit. So it doesn't have to be a general purpose quantum computer. If you can do that, then we have shown that in this small example, you get some quantum sort of communication advantage. And we hope in the future we can actually analyze in more generality, like all codes with 3 factor graphs, and see if the optimality still holds. And another interesting question is, we saw that today's operations are noisy. So even if you build this photonic quantum computer, if your gate fidelities are not perfect, then does this advantage still persist? It's an interesting question. And finally, the like sort of funny thing here is that we saw that BP is motivated by sort of bitwise maximum a posteriori decoding. So it's bitmap on 3 factor graphs. But the goal of this quantum algorithm, so belief propagation with quantum messages, is actually not clear, because in the quantum case, a posterior is not very well defined. So if you want to define a posterior distribution, then you have to have some observation of the data. But in the quantum case, you have to measure if you want to get some observation. And we know that measuring each qubit is suboptimal. So it's sort of a loop, and it's not clear if there is a good definition of a posterior by which we can say that this BPQM is doing sort of posterior marginal computation. All right, I'll leave it at that. Those are my references. Thank you.